Does the cosmos go on forever? Is an age-old question in philosophy and science. The observable universe is finite in that it hasn't existed forever. It extends 46 billion light years in every direction from us. But what lies beyond the observable universe? What we know for certain is that the universe is bigger than we observe it to be. Essentially because the farthest edges of the universe we can see don't look like edges at all. The observable universe is still huge, but of course it has limits. That's because we know the universe isn't infinitely old. We know the Big Bang occurred some 13.8 billion years ago.
We have a thing called the Sloan Digital Sky Survey, which maps the positions of galaxies. So you know how much of the sky you've surveyed, and you know how many galaxies you counted, and then you can spread that across the wider universe. And you get this picture of a vast and possibly infinite universe. We know that the universe, or very strongly suspect, that the universe is much bigger than the piece we can see. So we have good reason to think that's the case. Whether it's infinite or not is another question. Can you picture infinity? Well, no one can picture infinity. We say the universe began 13.8 billion years ago. So that's a measurement, because we can measure the speed that all the galaxies are flying away from us, essentially. So you can run time backwards, if you like, so to find out when they were all on top of each other. It's quite a simple measurement, and we've done that. So we say the universe began 13.8 billion years ago. But actually, all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence. And that means that actually the universe could have always been there, eternal. When I talk to people sometimes, some people get upset about that. Some people would rather it had a beginning. The idea that it might have been around forever is more frightening somehow than the fact that it began. And it's interesting the way that people's minds work.
The universe is huge, but it is only with recent discoveries that we can realize how inconceivably immense the universe, or even multiple universes, may actually be. Eternal chaotic inflation, which generates multiple universes, builds from the theory of cosmic inflation. Although inflation is generally eternal into the future, it is not eternal into the past, Alan Guth detailed in a paper published in 2007. New inflation does not produce a perfectly symmetric universe due to quantum fluctuations during inflation. The fluctuations may cause the energy and matter density to be different at different points in space. Quantum fluctuations in the hypothetical inflation field produce changes in the rate of expansion that are responsible for eternal inflation. Those regions with the higher rate of inflation expand faster and dominate the universe, despite the natural tendency of inflation to end in other regions. This allows inflation to continue forever. Modern physics has radically changed our picture of the known cosmos. It has offered us not only glimpses of what the future of the universe may look like, but it has also offered us a view for the overall shape of the universe itself.
From the theory of inflation, the best way to explain the universe, the properties that we see, is that it's very much bigger than the piece we can see. So for example, we measure space to be what's called flat. So if you imagine slices of space, let's imagine slices of them at different times. So you just slice the universe, and it can have a geometry, right? It can be flat like a tabletop, or it could be curved like a sphere, or it could be curved in the opposite direction, sort of like a saddle or a bowl. And we can measure that. And when we measure it, we see it's absolutely flat. And that's a very unusual thing for it to be like, because what Einstein's theory says is that the shape of space, that the curvature of space is determined by the stuff that's in it. That's basically Einstein's theory of general relativity. Put stuff in space and it curves it and bends it and warps it and stretches it and so on. And what we find is that there's precisely the right amount of stuff in the universe to have a completely flat universe. The explanation, the most favoured explanation for that, is the universe is way bigger than the piece we can see.
Because we cannot observe space beyond the edge of the observable universe, it is unknown whether the size of the universe in its totality is finite or infinite. Estimates suggest that the whole universe, if finite, must be more than 250 times larger than the observable universe. Astronomers calculate the age of the universe by assuming that the lambda-CDM model accurately describes the evolution of the universe from a very uniform, hot, dense primordial state to its present state and measuring the cosmological parameters which constitute the model. Over time, the universe and its contents have evolved. For example, the relative population of quasars and galaxies have changed and space itself has expanded. Due to this expansion, scientists on Earth can observe the light from a galaxy 30 billion light years away, even though that light has travelled for only 13 billion years. The energy from the Big Bang drove the universe's early expansion. Since then, gravity and dark energy have engaged in a cosmic tug-of-war. Gravity pulls galaxies closer together. Dark energy pushes them apart. Whether the universe is expanding or contracting depends on which force dominates, gravity or dark energy. Besides dark energy, there is also dark, mysterious stuff that fills the universe that no one has ever seen. This hypothetical form of matter, thought to account for approximately 85% of the matter in the universe, is also known as dark matter. But we have yet to understand what it actually is.
So we look out into the universe and we see that there's a lot of stuff there that's interacting gravitationally, but is not interacting strongly with the matter out of which we are made and the stars are made. So it's almost certain that that's some form of particle. That fits beautifully. And we see lots of different observations of the way galaxies rotate and interact. And even that oldest light in the universe, the so-called cosmic microwave background radiation, we see the signature of that stuff in that light as well. So we think that there's some other particle out there. And to be honest, we thought we would have detected it, I think, at LHC. We have lots of theories called supersymmetric theories that make predictions for all sorts of different particles that would interact weakly with normal matter. And yeah, I think it's broadly seen as a surprise that we haven't seen them at LHC. So that just may well mean that either they're a bit too massive, so we need more energy to make them, and we just haven't quite got enough, or we're not making enough of them often enough to see them, which is one of the reasons we're upgrading the LHC.
We may never have the answer to the question, is the universe infinite? Or if it does, have an actual boundary. What we do know, however, is that the observable universe is stupendously large in volume. The vast amounts of space includes anywhere from 200 billion to 2 trillion galaxies, according to varying estimates, and each galaxy has, on average, about 100 billion stars. These gargantuan numbers boggle the mind and are awe-inspiring when we look into the night sky and try to grasp the ungraspable volume of the universe.
This is the picture that Hubble took, and you see that it's anything but empty. It's called the Hubble Deep Field image. It's one of the most important and fascinating images in the recent history of astronomy. It's not empty, it's got lots of structure, lots of points of light in, and virtually every one of them, over 10,000 of them, are actually galaxies, distant galaxies. So they're not stars, they're galaxies. Now those galaxies on average have, 100,000 million stars like our sun in them, at least. So 100,000 million stars in each one of those 10,000 blobs. The most distant object in that image is 13.2 thousand million light years away. Now, light travels at 300,000 kilometers per second, 186,000 miles a second. And at that speed, it's taken over 13 billion years to travel from the most distant object in that image to Earth, to the Hubble Space Telescope. Now, when you think that the Earth is only just under 5 billion years old, it means that most of the light from most of the galaxies in that image began its journey to Earth before there was an Earth. And for some of the most distant galaxies there, they were over halfway here when the solar system was just a cloud of gas and dust. It hadn't yet coalesced into the sun and the planets and moons of the solar system. So imagine what that looks like. Imagine what that looks like when you extend it over the entire sky. Well, this is a beautiful map of the observable universe. Every dot on that map is a galaxy with 100 billion stars like our sun in it, at least. You see that the structure in there, they're not randomly distributed. It's very interesting. We're beginning to understand where that structure came from. Just to get some sense of scale, that little line up there, that's the 1 billion light year line. So light takes 1 billion years to travel from one end of that line to the other. This is the observable universe. This is the number of stars we know from observation are in the observable universe at the moment. 30,000 million stars. just like our sun, some bigger, some smaller. 350 billion large galaxies, 7,000 billion smaller dwarf galaxies. That's the observable bit of the universe.